let's continue. Our second speaker for this afternoon is Yue Yu, who is going to tell us something about symmetry.
Yes.
Okay, he will write the title.
Thank you very much for the introduction, and I would also like to thank the organizers for inviting me to Miami. The title of my talk is Gluing Holomorphic Cylinders. The reference is on archive. So here is the plan of my talk. I'll start with a statement of the theorem. Then I will review the counting of cylinders in log Alabi surfaces. After that, I'll explain the gluing formula. And in the end, I will talk about a conjectural relation with the notion of broken lines in the sense of a gross hacking peel. So let's start. We start with Y, smooth projective surface. Over the complex numbers, and D inside Y, a singular nodal curve of class minus ky, the anticanonical class. So here's the picture. We have Y and D, singular nodal curve of anticanonical class, like this. D. And we take X to be the interior, Y minus D. So X is log Alabi. And I denote Xk to be base change of X from C to K, where K is the formal Laurent series field. So now Xk is an algebraic variety over this non-Archimedean field, and we can consider analytification of this variety. So I denote Xk analytic, Berkovich's analytification. If you don't know about Berkovich geometry, you can still follow the talk. Don't worry. I will explain more background on Berkovich geometry in my mini course at IIS. I think many of you are spending time at IIS. So here it is. I will explain more background on Berkovich spaces there. Okay. So what's good about this analytic space? Let me introduce one more thing. Let B be the dual intersection cone given by D, cone complex. So what does it mean? We have a D like this, and the B is just the cone over the dual graph. So B is this. B. Now, by the works of Berkovich, as well as the works of Tullier and Hubler, Rabinov, and Werner, we have the following thing. First, we have a canonical embedding from B to the analytic space. Embedding. And a canonical deformation retraction from the analytic space to B. So, proposition, what's the geometry of this retraction? So, proposition, let's look at the retraction map. Tau, so the last moment of the deformation retraction to B. This is an aphenoid torus vibration outside the origin in B. Proposition says that outside the origin, this map is some kind of torus vibration, and this is an example of a so-called non-Archimedean SYZ vibration.
Sorry, is that true even along the edges?
Yeah. It's proved. Yeah. In my paper, I proved that. Oops. So, this is an example of.
Don't again change the control, please.
Oh, this is bad.
No, it's not. The noise is, but it's okay.
I just want to emphasize this phrase. So now I can state our goal is to prove a gluing formula for holomorphic cylinders with boundaries on fibers of this non-Archimedean SYZ vibration. So, as you know, the motivation comes from mirror symmetry for Calabi-Yau, log Calabi-Yau surfaces. Okay, I'll draw a picture, heuristic picture for what we will be doing. We have the analytic space, xk analytic, and we have the map tau from this analytic space to B. B is the cone complex homomorphic to R2 of this map tau. And the proposition says that all the fibers outside the origin, they are aphenoid tori. And above the origin might be something complicated. And we are interested in holomorphic cylinders with boundaries on fibers of this vibration. So, for example, we are this cylinder or this is also a cylinder that we are interested. Given a holomorphic cylinder like this, C, so when we have a holomorphic cylinder,
Why did B become R2?
B is homomorphic.
It's union of curves.
Yeah.
So it's just one piece, you're focusing on one piece.
No, union, it's you have cone and you glue them together, it becomes R2, right?
I guess it's a non-trivial result that if you look at the look at the components of the divisor, it actually forms a closed cycle.
Yes, it follows from classification of sources.
So then it's not obvious that it's R2. You have to know this fact.
Yes, thank you for the remark. When we have a holomorphic cylinder, C inside the analytic space, we can look at its image by tau. When we take tau, we get a tropical curve. We call it a tropical curve inside B. So for this cylinder, for example, the tropical curve is this. It's just the image by tau. This guy. This is tau C, like this. And we see that this tropical curve has two boundary points corresponding to the boundaries of the cylinders. And if we take the path connecting the two boundary points, we get a single path. And this path, we call it a spine. It's just this path. Connecting the boundary point. So what we do is that given a spine, we can count number of holomorphic cylinders associated whose spine is L, and we denote this number. We denote this number by n of L. I will recall you how we get this number. So now,
Will you recall us what is a holomorphic cylinder in this one?
it's just the annulus mapping to the analytic space. So now I can state the theorem, gluing formula. So given a spine,
So L is the spine, or?
yes. Now, given a spine, I denote it by L3. Looks like this. L3, and then we cut it at the middle of an edge here. Cut it at the middle of an edge, and we get two spans, one on the left and one on the right, L1 and L2. So the theorem just says that we have n of L1 times n of L2 equals n of L3. So it just says that when we count cylinders like this, they can be glued together. Shorter ones can be glued to longer ones. Let me give more information.
The red cloth works really well.
Oh, maybe the next one I use the red cloth. Yes. So, yeah, it's really an intuitive result that the counting of the long one is the product of the counting of the shorter ones. I just want to say that it's not entirely precise because we also need to take into account the curve class of the cylinders. So a more precise statement involving curve classes is the following. Curves classes, we just think of it as some relative homology class of the cylinders. So it's number of so that's the precise statement. Beta 1 plus beta 2 equals beta 3. Thank you. Yes. So that's the precise statement, but for simplicity, I will omit discussions on curve classes for this talk. So now let's recall you how the number n of L they are defined. Review of cylinders. Since we want to count this kind of cylinders associated to a spine L, we want to look at the moduli space of all such cylinders. But unfortunately, one observes that the space, so given L, the space of holomorphic cylinders whose associated spine equals L is an infinite dimensional space. And the challenge is to extract a finite number from this infinite dimensional space. Is to get a finite number from this infinite dimensional space. The strategy is the following. So we have a spine like this. We have a holomorphic curve, holomorphic cylinder, let's say, like this. Since we are in analytic geometry, we can do analytic continuation at the boundaries. So our strategy is to impose an extra regularity conditions on the cylinders. So we impose regularity condition on the boundary of the cylinders in the following way. we ask that by analytic continuation at the boundaries, our cylinder extends all straight to infinity. So what do I mean? A priori, when we do analytic continuation at the boundaries, various things can happen. Like maybe they refuse to extend, or maybe they extend to very complicated shape. But we just want to ignore all this other behavior except those which extends all straight in this way. So by imposing this extra regularity condition, we obtain a closed rational curve. So in this way,
So you're requiring analytic continuation to exist.
yes, I'm adding this artificial, a priori artificial condition that we want it to come from a closed rational curve. But later, when we prove this gluing formula, you will see that we are, because now we are making some a priori artificial thing, but later you will see that the gluing formula, which is natural for cylinders, really holds with this regularity condition.
But can you characterize, of course, because then it's a continuum, shouldn't you be able to say something just about what's happening in the neighborhood?
Sure. Analytic continuation is determined by just on the neighborhood.
But
On the
this
very small
uses the
piece.
data of the fact that you live, the way you're phrasing it uses the fact that you live inside the.
But on the neighborhood, you can also easily see from the function whether it's like just look at locally how it's defined.
Okay.
It's just a more geometric way of saying. Yes, it's a good question because I mean, by asking this, you are thinking that whether it's really a boundary condition or something like not local. So yes, the answer is yes. Yes, it's just a condition on the boundary. Okay. So now by this condition, we reduce. So in this way, we reduce the problem of counting cylinders in the analytic space. It's reduced to the problem of counting this special kind of closed rational curves in the analytic space, the compactified X, which is YK analytic, whose associated spine is L hat, which is the extension of L to infinity. In order to count such rational curves, now it's an easier task. So we do the following. Let M L hat be the moduli step of rational stable maps with 3 marked points, such that the first and the second marked point goes to the boundary. Goes to the boundary. I will draw a picture if you are confused. And third marked point goes to a fixed point W in the analytic space, such that tau of W is one boundary point of our spine, and moreover, the associated spine equals L hat. So let me draw a picture. We have this and our B. So if we start with this, our L, we extend this spine to infinity or straight, by L hat. Then we just consider the space of rational stable maps with 3 marked points, such that the first, I consider with 3 marked points, such that the first and the second marked point goes to the boundary, and the third marked point goes to a fixed point in the analytic space which maps to the boundary of our L. Yeah, and theorem approved in 2015. First, this space M of L hat, this moduli stack, is a proper K-analytic stack. The properties. Second, M of L has a virtual fundamental class ML virtual hat of degree 0. So in that part, I used the classical construction of Berra and Fantacchi, as well as my joint work with Maulo Porta. And the third point is that the degree of this virtual fundamental class is independent of the choice of W. So in this way, as a consequence, by the theorem that we define the number of cylinders to be degree of this virtual fundamental class, and this is well defined. So here is a quick review of how the cylinder numbers are defined. Now let's go back to the gluing formula, because you see that the way to define the counting of cylinders, what we really want to count is this kind of cylinder with boundaries. But then, yeah, I made a trick to reduce this counting problem to the counting of closed rational curves. So after this trick, it's no longer clear whether we are actually still counting some open invariants, because it becomes like counting closed invariants.
So where are you using the fact that this is relative to
Virtual dimension.
And where are you using the fact that it's dimension 2, or is this true always? You started with the surface.
Yes, I started with a surface because this regularity condition is trickier in higher dimension. I know how to do it now, but during my thesis I didn't know how to do it. Okay. Yeah, so we have done this trick. It's no longer clear whether we are going to the wrong path or we are still counting this open invariance. So we want to make sure that this kind of counting really reflects counting of cylinders. So let's try to prove this gluing formula. Recall you the gluing formula. Oh, I just erased. So let me draw again. We have this long spine, which we call the L3, and we cut it into two halves. Left half L1, the other half L2. What we want is number of cylinders associated to L1 times number of cylinders associated to L2 equals number of cylinders associated to L3. So yes, so by this definition, what we want is equality between this degree of virtual fundamental classes. In other words, we want degree of times degree of so geometrically, let's see what means this equality. Geometrically, it means that the first part is the number of rational curves associated to the extension of L1, which I denote by L1 hat. And the second part is number of rational curves associated to L2 hat. And we want it to equal to number of rational curves associated to L3 hat. So let me draw a picture. We have L1 like this. And its hat is just extending this L1 to infinity. And this degree represents number of rational curves whose spine is this L1 hat. So geometrically, they are rational curves of this form. And similar for L2. We have L2 hat, we have L2, which looks like this. So L2 hat is extension, and the number of rational curves associated to L2 hat is of this shape. And finally, for L3, it's again the same thing. This is L3. We extend it to infinity, and we want to count a number of rational curves whose span is L3, and we want to get equality of these three numbers. So in order to prove this, we consider the following stack M of L1 hat union L2 hat, which is the modular stack of rational stable maps with in YK analytic with 5 marked points, such that the first, second, third, and fourth marked point goes to the boundary. The fifth marked point goes to a fixed point W in the analytic space, such that tau of W equals the cutting point. And the place where we cut the spine. And finally, we ask the associated spine to be equals the union of L1 and L2. So let me draw another picture. We have our L. This was our L3, and we cut it into two halves, L1 and L2. And then we extended L1 to L1 hat and L2 to L2 hat. So now we want to consider the modular stack of stable maps with 5 marked points, such that the first 4 marked points goes to infinity, and the fifth marked point goes to a fixed point, and then the associated span equals this thing. So if we draw a picture, the stable map that we are interested in for the moment looks like this. And we have marked points 1, 2, 3, 4, 5. Here we have the last marked point. Okay, and now let's recall that there we only have 3 marked points. Now we have 5 marked points. So, but rational curves with 5 marked points has modulus. We can consider M0, 5, and the modular space of rational stable 5-pointed rational curves. And inside there are 2 special points, M denoted by M and M prime, where M is and m prime is this one. So now let me state the next theorem. We consider the map phi that goes from our moduli space, this moduli space, M of the combined spines, to M0 phi, just taking stabilization of the domain curve. And the theorem says that there exists a connected analytic domain W inside M0 phi such that first this analytic domain contains the two special points M and M prime, and second that phi is proper over W. So as a corollary, we have, since the W is connected and phi is proper, as a corollary, we have degree of the fiber of phi over M equals degree of the fiber of phi over M prime. Now, one can prove a further proposition. So now maybe I write an observation. So we have this kind of thing. So an element in this fiber is a stable map satisfying this condition, plus the fact that the domain curve looks like this. And an element in that fiber is a stable map satisfying this, that, all these three conditions, plus the fact that domain looks like this. Now, there's an easy observation that for any stable map in this fiber and the other fiber, the irreducible component containing of the domain containing the fifth marked point always map to a point in the analytic space. Let me re-explain. So the observation just says that for any stable map whose domain is either this or that into the analytic space, this part is always crushed to a point. So we don't need to care about this part. All that that are interested are these bigger parts. Now it's easy to prove a proposition. So proposition, first degree of this guy, phi minus 1 let me recall you that this just means the number of stable maps satisfying these conditions plus the condition that the domain is this one. So this is equal to degree of M of L1 hat times degree of M of L2 hat. And by definition, this is just the product of the number of cylinders associated to the spines and L1 and L2. Oh, here I should add a prime. And the second part, degree of the same thing with M equals degree of M of L3 hat times degree of M of this dotted line and this straight dotted line. So this straight line. And fortunately, one can prove that this is always 1. So whenever the span is straight, the number of cylinders associated to a straight span is always 1. So this equals M of L3. Now we achieve our proof. Corollary plus proposition implies the gluing formula we want. I hope you all get the heuristic idea of the proof. But since everything is in non-Archimedean geometry, so in order to make it precise, it's still a bit long to present the proof. But the heuristic idea is easy.
Can I ask about this domain? Why
Yeah.
is this domain not all of M05?
The domain a priori can be all of M05, but I choose 2 specific points.
Yeah, but you need a very careful statement of the theorem that there exists a connected analytic domain.
Properties fails when you select a smaller, when you select a bigger W. I just select the W which is bigger enough to be connected and containing my 2 special
What
points.
should I have in mind for failure of properness? I mean, what kind of example? I mean, when you say properness fails, you mean you have an example where it fails?
Yeah, yeah.
So what is that?
So, for example, if you look at a domain curve, which is like this, so here these 2 points you can smooth it, and it will become something like this. Then it can become like this part can grow longer, and when it's longer than the edge you cut, it fails. Okay, so we achieved our gluing formula, and it's really reassuring for us because it shows that our a priori artificial condition on the boundaries is not too bad. It's still really reflects open curve counting. So yeah, and using this gluing formula, one can prove the wall crossing formula for these counting numbers conjectured by conservative and Solomon of this remark. The gluing formula implies will imply the wall crossing formula conjectured by So let me end my talk by presenting a conjectural relation between the counting of cylinders with the work of gross hacking Kiel with the notion of broken lines. So actually, they are intimately related, and this non-Archimedean counting of cylinders, actually, they are conjecturally, they give a geometric interpretation of the combinatorial notion in the works of gross hacking Kiel. So here is the precise conjecture, first part. First, I would like to say that the gluing formula implies that no matter how a spine is complicated, we can always cut it at many places to decompose it into small, simple spines. So if I have a spine which is very complicated, have lots of bends, one can always cut it. So cut it into spines, simple spines, with just let's see, with only one bend. And by the gluing formula, it says that this number equals the product of the number of holomorphic cylinders associated to all the simpler spines. So this suggests the following conjectural relation with broken lines. It suggests the following relation with broken lines of gross hacking Kiel. So let me mention that here I'm illustrating the relation between broken lines in the work of gross hacking Kiel, but broken lines were invented also earlier than that work. So I think the ideas were also suggested by in the work of Gross Siebert and also by Kansevich Soberman, Abu Zaid Muhammad, I guess. So yeah, here I just speak broken lines in this particular work, GHK. And so in GHK, they look at exactly the same context, YD, and also the base B. And on the base B, we have the so-called the canonical scattering diagram. Of GHK. Looks like this. This is B. And there is a scattering diagram consisting of a lot of rays. And each ray is attached to some function responsible for the wall crossing transformation. And then let me recall you that a broken line is a map. Oh, the colors are too similar. A broken line is a map it's a map gamma from minus infinity 0 to B, piecewise linear, that bends only at the rays of the scattering diagram. Moreover, each segment is associated there is some monomial attached to each segment, and the whole thing is compatible with the scattering diagram in some sense. So now let me state the conjectural relation. So in particular, at the last domain of linearity, we have a monomial associated, and I denote by C times Z to the power Q, the monomial attached to the last domain of linearity of gamma. So this C is a rational number, and this Q lives in some local system in GHK paper. It's long to recall. I just mentioned that we can decompose Q into beta plus lambda for beta inside the cone of curves of Y, and lambda in some local system, which is roughly the tangent space, tangent lattice of the base. So now the conjecture is that the number of cylinders denote L of. So such a broken line, gamma, gives rise naturally to a spine of exactly the same shape, to a spine which I denote by L of gamma. So the number of cylinders associated to the spine L of gamma and the curve class beta is equal to this coefficient C in the work of Gross, Hack, and Kiel. So I hope that this conjecture, it's not difficult to prove, and then it gives a geometric interpretation of the combinatorial story, the beautiful combinatorial story of Gross, Hack, and Kiel. Thank you very much for your attention.
Okay, any questions?
Did you say the gluing formula helps you to get rid of the regularity assumption or something?
No, it's just that once we add the regularity assumption, because if we say we just naively count the cylinders, then the gluing formula is obvious. It's just like going, like we have 3 places, and going from 3 places A, B, C, and going from the number of ways going from A to B times the number of ways going from B to C.
You made a comment about both gluing formula and regularity assumption. Like, can you get rid of the regularity assumption? Or is there...
No, the comment is just that once we add the regularity assumption, the gluing formula is no longer obvious. It becomes a theorem that one can prove, that one should prove. And the regularity condition is essential. Without that, we don't get a well-defined counting.
Other questions? Let's thank Tony again.